Welcome back. We are at physical layer. In this video, we will learn about encoding and modulation. By the end of this video, you will know how to encode bits into digital signals and how signals are sent over links. In a previous video, we discussed physical media and we saw that physical media carries analog signals. And therefore we need to convert bits into analog signals before sending them over links. This process of converting bits into analog signals is carried out by network adapters. Network adapter is basically a hardware that connects a node to a link. It has signaling elements that encode bits into signals at the sender end and decode signals into bits at the receiver end. And as this diagram shows, bits flow between adapters and signals flow at the link. Network adapter is also known as network interface card, or NIC for short. The functionality of network adapter layer is implemented by encoding and modulation layers. Encoding layer converts data to digital signal and modulation layer converts digital signal to analog signal. In baseband modulation, the analog signal is sent as it is, and therefore some people even refer to encoding as baseband modulation. In the case of passband modulation, we use a high frequency carrier signal and we modify the parameters of that carrier signal using this digital signal that we obtained in the encoding process. And then we send this transmitted, then we transmit this modified carrier signal. The parameters of carrier signal that we typically modify are amplitude, frequency, phase, or a combinations of these three. And we will discuss in detail some of the passband modulation schemes. We begin with encoding. The first encoding scheme that we are going to discuss is called NRZI. It stands for non-return to zero. In this encoding scheme, we assign high signal element to 1 and low to 0. And high signal element, for example, could be plus 2 volts and low could be 0 volts. And so suppose we are sending this sequence of bits 0, 0, 1, 0, 1, 1, 1 and so on. And for this sequence, the NRZ encoding would be low followed by low, then a transition to high, and then again transition to low because we are sending 0, and then transition to high, and it remains high for all these consecutive ones, and then fall back to 0, and then again to high, and so on. There was an encoding scheme called return to 0, and that's why its name is non-return to 0. In return to 0, the signal always return to 0 after half clock cycle. So in the case of 1, it won't remain high for the entire clock cycle, but it would drop to 0. NRZ does not work well when the data contains long strings of zeros and ones. It turns out that receivers keep an average of the signals, and they use this average to distinguish low from high. When a signal is sufficiently lower than the average, the receiver would decode it as 0, otherwise it decodes it as 1. Too many consecutive zeros or consecutive ones cause this average to change, and that results in difficulty in distinguishing 1 from 0, and this is called baseline wander. Suppose we encode high with plus 2 volt and low with 0 volts. And if the data has roughly equal number of zeros and ones, then the average is going to be around plus 1 volt. And so if the received signal is lower than 1, then the receiver would decode it as 0, and if it's sufficiently higher than 1, then it's going to decode as 1. Now if we get too many ones, then this average is going to shift towards plus 2 volts. So this happens when you have too many ones, and this causes the gap between high and average to shrink, and that makes recognizing ones harder and harder. Similarly, if you get too many zeros, then the average is going to shift more and more towards the low value, and then decoding 0 gets harder and harder. And that's why baseline wander is undesirable. Another problem caused by long strings of consecutive zeros or long strings of consecutive ones is that the sender and receiver clocks can get out of synchrony. And synchronization is important because every clock cycle, the sender transmits a bit and the receiver recovers a bit. And therefore, sender and receiver clocks must be synchronized because they must agree on bit boundaries. However, a fundamental problem with clocks is that clocks tend to drift. And so, to maintain synchronization, one may think of sending clock signals separately. However, just using a separate cable for clock signal is not practical because of cost considerations, or we can't do in wireless. Instead, receiver derives clock from signal transitions. The receiver clock maintains synchronization with the transmitter clock using the transitions from high to low and low to high. And therefore, sending too many ones or too many zeros does not give the receiver clock the opportunity to derive the clock from the signal transitions. When the clocks get out of synchrony, it may happen that the sender sends, let's say, 100 zeros, all consecutive, but the receiver may wrongly infer that 99 zeros were sent, or 101 zeros were sent. NRZ suffers from both baseline wander and clock recovery. NRZI encoding, which stands for non-return to zero inverted, is an improvement over NRZ. In NRZI, 1 is encoded as a transition. This transition could be from low to high or could be from high to low. And we encode 0 as no transition. Let us look at this example again. So this blue line indicates this NRZ encoding for this bit sequence 00, 10, 111 and so on. So I'm going to show the NRZI encoding in red. The NRZI encoding for 0 starts at low, then another 0, low. When there is a 1, we make a transition, and we make the transition at the rising clock. So the transition is from low to high. And then after 1, there is a 0, so we make no transition. And then 1, we make a transition, so in this case from high to low. And there is another one, so the transition would be from low to high, and so on. And so note that although we had this long string of 1 in NRZI encoding, we had plenty of transitions. But for this long string of zeros, we basically have no transition. So NRZI solves the baseline wander and clock recovery, but only for consecutive ones. And therefore NRZI is used along with another encoding scheme called 4B5B, which we will discuss soon. The next encoding scheme that we will discuss is called Manchester encoding. This encoding solves the problem of baseline wander and clock recovery for any kind of bit sequence. In Manchester encoding, a bit is encoded as XOR of the NRZ encoding, or you could think of as XOR of clock. And so zeros would basically reproduce the clock, and ones would be just inverted clock signal. So this blue line here shows the clock, and the Manchester encoding is shown below that. And so the bit 0 is encoded as a transition from low to high, and then another 0 from low to high, and then 1 as high to low, another 0 from low to high, and then 1 as high to low. We have 4 ones, 4 transitions, high to low, and so on. There is one disadvantage of Manchester encoding, and the disadvantage is that it doubles the rate of signal transitions on a link. Here I have drawn Manchester encoding for 3 zeros. As you can see, the signal here makes 5 transitions, and that's undesirable because the receiver gets half the time to detect each pulse. So the rate at which signal level changes, it's called link's baud rate in old terminology, and it's these days it's called symbol rate. In Manchester encoding, the baud rate is twice the bit rate, and ideally it should be the other way around. And so Manchester encoding is only 50% efficient. 4B, 5B encoding is the last one we will look in this video. Remember, NRZI had the problem that it fixed the baseline wander and clock recovery for consecutive ones, but it couldn't fix the problem for consecutive zeros. And this 4B, 5B encoding fixes the problem of long string of zeros, and it does so by encoding every 4 bits of data into here I have shown some of the encodings of 4-bit data to 5-bit code. The 4 zeros is encoded as 4 ones followed by a 0. 3 zeros followed by 1 is encoded as 01, 001, and so on. So let's look at this example of 4 ones followed by 4 zeros followed by 0010. 4B, 5B will encode this as first. For 4 ones, the code is 3 ones followed by a 0 followed by a 1. Then for 4 zeros, we have this code 4 ones followed by a 0. And then for 0010, it's 10100. And so although we had a string of 6 zeros in our data, but we don't have any of long strings of zeros, but we do have long string of 1 here. But that's not a problem because we are going to send it using NRZI, and NRZI makes transition for all ones. Note that for these 32 possible codes, we are using only 16 in encoding, 4B, 5B encoding of our 4-bit data. And so another 16 are left. Out of that, some are used as control messages. And some of, those control messages are shown here, like a sequence of ones indicates line is idle, and sequence of zeros indicates line is dead. 00100 indicates halt, and 11 followed by 3 zeros indicates the start of frame. In passband modulation, a high frequency carrier signal is modulated to transmit the baseband signal. You can think of carrier as some high frequency sinusoid. The result of passband modulation is that a bHz baseband signal is shifted to some S Hz to S plus bHz passband signal. We modulate the amplitude, frequency, and phase of the carrier signal according to the digital signal. In amplitude shift keying, or ASK, we modulate the amplitude of the carrier signal. Here different amplitudes represent high and low, or a 1 and a 0. Consider this example of NRZ encoding of 01, 0110, 01, and so on. This is amplitude shift keying modulation of this digital signal. For 0, we have absence of amplitude. For 1, we have high amplitude. For 0, again absence. For 1, high, and 1 high, and so on. Frequency shift keying, or FSK, modulates the frequency of the carrier signal. In this figure, FSK is shown on this line. So for 1, we are representing 1 as high frequency and 0 as low frequency. And so again for 0, we have this low frequency carrier. For 1, high frequency. For 0, low frequency. For 1, high frequency, and so on. And the third, phase shift keying, or PSK, modulates the phase of carrier signal. Again, this is representation of this digital signal using PSK modulation. Here 1 is represented by 0 degree phase, and 0 is represented by 180 degree phase. And so let's again consider that example. For 0, we have the sinusoid, and for 1, we shift this phase, so it begins at 0 degree, and then for 0, the phase is 180 degrees, so again it goes from 180 degrees all the way to 0. And for 1, again from 0 to 180, but then we have another one, and so we continue from 0 to 180. So we have a wave that continues on, without change of phase. In all these 3 examples, the signal element has 2 levels, 2 different amplitudes, 2 different frequencies, 2 different phase, and each signal element therefore represents 1 bit. All of these ASK, FSK, and PSK can be generalized to multi-level signals, where each signal element encodes multiple bits. By the way, this version of PSK is known as BPSK, which stands for binary phase shift keying. Another generalization is to combine these. For example, There is a modulation called QAM, stands for Quadrature Amplitude Modulation, that combines amplitude and phase, and we will see a little bit more detail about QAM in the next slide. Quadrature phase shift keying, or QPSK, generalizes BPSK. QPSK encodes 2 bits per symbol by using 4 phases. These diagrams are called constellation diagrams. They show amplitude and phase combination of each symbol by dots. So this is a constellation diagram for QPSK. QPSK uses 4 phases: 45 degrees, 135 degrees, 225 degrees, and 315 degrees. All of them have the same amplitude. Amplitude is represented by the distance from the origin, and phase is represented by this angle. Since there are now 4 symbols, each symbol can encode 2 bits. For example, 45 degree phase could encode 00, 135 could encode 01, 225 11, and then 315 10. QAM generalizes QPSK to combined variations of both amplitude and phase. This is constellation diagram of QAM 16. Each of these points differ from others in either amplitude or phase, or both. In 16 QAM, each symbol can encode 4 bits because we have 16 possibilities. There exist higher order QAMs where each symbol encodes 7 more bits. The trade-off is that one needs more sophisticated electronics to decode modulations where each symbol encodes more and more bits. This is summary of this video. Network adapters convert binary data to digital signals. It's a hardware. It has another name called NIC, or Network Interface Card. The functionality of network adapter can be thought of implemented in 2 layers. First is encoding layer, and the function of that layer is to convert data to digital signal. And then there's modulation layer, and the function of that layer is to convert digital signal to analog signal. Next, we saw that signals on a link need to make frequent transitions, and this has to be done in order to avoid baseline wander and loss of clock synchronization. And we saw that the combination of NRZI and 4B5B modulation ensures that long runs of zeros or ones don't occur in the encoded signal, and passband transmission involves modulating a high frequency carrier signal where we modulate the amplitude, frequency, or phase, or a combination of these of the carrier signal. You can find more details of the topics we covered in this video in Peterson and Davis book, section 2.2, and Tenenbaum and Weatherall's book, chapter 2, section 5. Here is a quiz for you. Which of the following options are correct? You might want to pause this video. Here is the answer. The correct options are B, C, D, and F. A is wrong. In NRZI, how 0 is encoded depends on the transition that previous one made. So 0 could be encoded as either low or high. B is correct. Manchester encoding is 50% efficient. C is also correct. In 4B 5B encoding, we map 4-bit data to 5-bit code. D is also correct. In wireless transmissions, we have to use allocated spectrum, so these transmissions are passband. E is wrong. In QPSK, we have 4 symbols, so therefore each symbol can encode 2 bits and not 4 bits. F is also correct. In QAM modulation, these symbols are represented by variations of amplitude and phase both. That's all for this video. See you next time.